Hello guys, and Assalamualaikum warahmatullahi wabarakatuh. Today, we are going to present to you about application of differentiation related rates. We are from CDCS 1121B and we are from Group 4. My name is Muhammad Hafiz Aiman bin Muhammad Hanafi and I'm with two other group members which is Muhammad Hafiz Aikal bin Muhammad Amir that is going to introduce to you guys what is related rates and their use in our life. The other one is Edwin Fahan and Ihsan Husaini Vincent that will be explaining to you guys about steps on how to solve a problem with related rates.
Assalamualaikum and thank you Haziq for the introduction. First, we will dive into what is related rates. Calculus's fascinating notion of related rates enables us to understand the complex dance between changing quantities. Consider it as a kind of mathematical detective tool that may help us decipher connection between seemingly unrelated objects, even while they are in constant state of flux. To unravel the mysteries of how the change of one quantity affects the change of another is like possessing a superpower. Commonly, in related rates, we use the formula of dy over dx equals to dy over du times du over dx, on which the du will cancel out, giving us the dy over dx. After understanding the concept of related rates, we might question ourselves, why did we need to use related rates in our life? To begin with, we can investigate the dynamic relationship between variables in the domain of related rates. When we came across situations where there are change in one quantity is entwined with the change in another, this idea becomes especially fascinating. Think of it like trying to solve a puzzle when the components are always moving. This is typically done through implicit differentiation and application of the chain rule on which we have learned on the previous topic. For example, related rates are often implemented in solving problems involving geometric shapes, motion, fluid flow, and more.
Now I'm going to read an example of a problem which is air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cm cube per second. So the question was, how fast is the radius of the balloon increasing when the diameter is 50 cm? Next, I am going to explain how to solve this problem. First of all, we need to identify the information given, which is the rate of increase of volume air is equal to 100 cm cube per second, and the rate of increase of radius when diameter is 50 cm. So we know that the radius of a circle is half the length of its diameter. Right now we have the diameter, that means we can find the radius by dividing the diameter by 2. So the radius of a circle is 25 cm. Then we need to know that rates of change are derivatives. Here, the rate of increase of volume with respect to time is dv over dt, which is equal to 100. And the rate of increase of radius with respect to time is dr over dt. That is not given in the information. After that, we should know that the volume of a sphere is equal to 4 over 3 pi r cubed. Next, we can construct an equation that relates both the constant and variable quantities, which is v equal to 4 over 3 pi r cubed. By using this formula, we can differentiate both sides of the equation with respect to t. So we get dv over dr is equal to 4 pi r square. Next, we can apply the chain rule to relate both derivative that we have. So the equation would be dv over dt equal dv over dr times dr over dt. For the last step is we can now solve for the unknown quantity. Substitute all the value of derivatives that we have into the chain rule. So the equation is dv over dt equal to dv over dr times dr over dt. We can now substitute dv over dt to 100 and substitute dv over dr to 4 pi r square. Next, we can rearrange to solve the equation. After that, we get dr over dt is equal to 100 over 4 pi r square. Next, we need to substitute r to 25, so it becomes 100 over 4 pi times 25 square. Solve it and we will get the final answer is 1 over 25 pi.
In conclusion, the radius of the balloon is increasing at the rate 1 over 25 pi, which is equivalent to 0.0127 cm per second when the diameter is 50 cm.
In the slide, we use some of reference from external sources. One of it is slide illustration, and on another is a book called Fundamentals of Calculus. Here is the citation for our references.